So, hello and welcome to another video from sickmaths.co.uk, where you can find lots of free GCSE and A-level maths videos. Right, so this video is basically a summary of everything you need to know, but not just that. I've done small things like rewritten formulas in a more useful way than you get in the formula book. You must have realised that sometimes they write things in the formula book that is so badly written and so difficult to understand, or in a way that's not actually very useful. Okay, so I've written it in a more useful way, and basically I haven't picked out everything in the formula book, so that would be really useless. I've picked out stuff you need to know for the C4 modules, which aren't necessarily just in the C4 section. Okay, they're basically spread out amongst the different modules. So that's that, and I've also written the stuff that's not in the formula books and you really need to memorize. So basically this is a really handy little video to tell you what you need to know for this module. So let's get on with it. In the formula book, into the C2 section, you're told about how to expand a binomial, do a binomial expansion, and I made a small change. Instead of just writing 1 plus x to the power n, which never happens in a C4 module, you never get 1 plus x to the power n, you always get 1 plus ax to the power n. Okay, now some people would realise it's supposed to be that, but I'm making it nice and simple and clear, so you know everything you actually need to know. So, and then it expands like this, of course, and what else do I tell you? Of course, the expansion goes on and on and on indefinitely. And what else? Of course, hopefully you know 3 factorial means 3 times 2 times 1. Okay, and basically these things are valid. Okay, this expansion is valid for if n is less than 1, which it usually is in C4, or it's a fraction. Basically, therefore, ax, the modulus of ax, has to be less than 1. Okay, which is how, this is what you get for C4 kind of questions, right? And again, in the actual, what's it called, formula book, it's not that clear. Okay, it's written in a more complex way, not everybody can understand. Anyway, let's move on. Again, we've got some identities here, which I've written in a slightly simplified way. Instead of writing plus, like in this one, normally it's written as plus or minus, minus or plus. Some people get confused about that, although you should try to understand everything in the formula, to be honest. Okay, but this is just a simplified, get it down your throat sort of stuff. So sine a plus b equals blah blah blah. How is this really useful? Because you can derive this formula here, sine 2x equals 2 sine x cos x. And how do you do that? Very quickly, you can just say if that was x and that was x, that means these would all be x, therefore you get sine x cos x plus sine x cos x, which is basically 2 sine x cos x. So that's very easy to derive, save you memorizing it straight away, although if you do it enough times, you really, if you should be practicing this so much that you eventually learn it anyway. Again, if I convert the a's and b's to x's, you get cos x minus sin x, which obviously converts to cos squared x minus sin squared x. And using this stuff which you have to memorize, which you should have memorized by the time you got to C4, okay, you just basically, for example, if I want to get to this one here, from here, all I do is replace the sine squared x with 1 minus sine squared x, but just rearranging this, isn't it? Okay, which basically gives you 2 cos squared x minus 1. I'm not giving you the absolute details of how you do it, I want you to think a little bit, otherwise I'll take too long making this little video as well. Anyway, and also, from here you can jump to here, replace the cos squared x with the 1 minus sine squared x, and you get this. Okay. What else is really useful? Yes, I mentioned this many times in my videos so far. Basically, if you are told that tan x differentiates to sec x, then obviously sec x integrates to tan x. So those are really useful. If they want you to integrate cosec squared x, okay, that integrates to minus cot x, just times both sides by minus 1. Move that minus 1 or minus to the other side. So that's a little tip there. Right. Don't worry about trying to integrate that to that. That's a bit confusing, isn't it? Yeah, that's just there for you to remember that that differentiates to that. Yeah, that's the quotient rule. Hopefully you remember that. You have to memorize the product rule, by the way. Yeah, but the quotient rule is a little bit longer. Product rule is so obvious to remember. I don't want to jump to that side yet. Anyway, and then you've got by parts, although that's incredibly simple to learn. There you go. It's there for you. You don't have to memorize it. Okay, let's go down to the memorize this section. So this is stuff in the formula book. This is stuff you really have to memorize, or can be derivable from that. But anyway, so vector of a line. So vector equation of a line is written like that: the starting point of the position vector plus a variable like lambda or mu usually. Lambda and mu are the typical letters, times the direction variable, which kind of makes, direction vector, which makes sense, right? You start from a point and you go off in a direction infinitely, one way or the other. Okay, that effectively gives you a line. Okay, but obviously, if you go to the vectors video, I've described that in more detail. This is actually the only thing you really have to memorize that is new. That's something you have to understand, I suppose, but this is the only formula you have to learn. This stuff here, which is also part of vectors, is part of your part of something you really should have learned at GCSE in Pythagoras. Okay, it's just about the physical size of things, where your vectors are really just like your coordinate axes. That's like your x-axis, your y-axis, and your z-axis. Anyway, so what does the formula say? Very briefly, if these two are vectors, yeah, that's why you got squiggly lines. By the way, you write squiggly lines underneath them when you put in handwriting. When you see in print, it's just written in bold. There's different ways of doing things. Anyway, so A dot B means the dot product, which obviously I explained in the vector section of the C4 book that I've written, times is equal to the modulus of A times the modulus of B times cos the angle between them, where theta is the angle between the two vectors A and B. We've just talked about this really. The modulus of this is basically that, yeah, very simple, and of course that is derived from Pythagoras. Right. This is telling you something very simple about partial fractions. If you want to break up a nice big fraction which has these factors on the bottom, you can break it up like that basically. However many factors you have on the bottom, that's how many different fractions you can make. So I've only got one there, so I put one fraction here, but what I'm also demonstrating is if you've got a squared factor, okay, then that actually creates two fractions, which is one with a linear version of it and one with a squared version of it, squared denominator. So that's that. These things you should have learned from C2 very long time ago. Sine whatever, blah, blah, blah. You can read that by yourself, of course, and we've talked about this stuff already, very important. Tan squared equals sec squared minus 1, cot squared equals cosec squared minus 1. Not that hard to derive, actually. Just derive it from this, think about it. Like if I divide everything by cos, guess what happens, and then rearrange it. Yeah, just think about that. What else is there? Differentials. So these are very important differentials you really need to know. So e to the x differentiates to e to the x, etc., etc. One thing I haven't mentioned is stuff like e to the kx differentiates to k e to the x, but that's stuff you have to understand. It's called the chain rule. Okay, so I wanted you to at least have the absolute basics from which you can move forward, you see. So you have to, I don't want to tell you all the different things that could be possibly derived from this. I don't want to show you the chain rule versions of these, yeah? Like in the formula book, they have the chain rule version of this, but I thought, why have you got the chain rule version of some of these things and not for the others? Yeah, it doesn't make sense. So that's why I put it slightly different to the formula book. This way it's easier to memorize, I think, when it's kept simple as well. Right, and besides this is the product rule, by the way. If you've got two things multiplying, the differential is, that dash means the differential, right? I hope you know that. So you've got an f dash x means the differential of fx, of course. So UV get. But I'm not going to read that for you. What else is really useful? Basically, this is how to integrate something which is written with parametric equations. This is a very simple trick. Change the dx to dx by dt. Yeah, basically it's a kind of substitution. Okay, of course there's loads of other things you have to substitute for the y as well, and the limits if there are limits if you're doing parametric equations. Okay, and also this is also for parametric equations, very nifty trick. If you want to find the gradient of the line on a parametric equation, what do you do? Well, you need dy by dx, don't you? But how do you find that using parametric equations, which are written in terms of t? You simply do dy by dt divided by dx by dt. Now, if you imagine like that, like a fraction, flip it upside down, and the dt's cancel, you just get dx by dt. Very easy to do. I'm not going to tell you more than that because you have to watch the parametric video if you really need to. And of course there's the old log rules, which aren't written down anywhere, so you just have to memorize them. Very simple. If it's adding logs, you times those x and y bits, yeah. And if you're taking away the logs, you divide instead. It's just like your indices rules, yeah. When you times things together, you add the powers. Remember, logs are about focusing on the indices, so it's not surprising it's the other way around. You're adding the powers, you're taking away the powers. Okay, if you got a power of a power, oh no, it doesn't really apply to that really. But anyway, well, it does sort of, but anyway, and then of course this rule is if you got a number in front of the log, you can bring it up and make it a power. So that's it really.